Okay, so we are going to be looking at stress, which many of you are probably familiar with at this point in your grade 12 life. And last day we were dealing with the stress of changing concentration. Today we will be dealing with the stress of changing volume or pressure, and we will be looking at this from both a rate perspective and a Le Chatelier's principle perspective. We are going to start with rate. So we have this reaction here, and it's all gases. All the reactants are gases, all the products are gases. So we can do things like if we change the volume, we're going to be changing the pressure. Yes, because everything's a gas. If we decrease the volume, what happens to the pressure? Does it increase, decrease, or stay the same? Yes. It increases, yes. Does anyone want an explanation of why that is so? Yes. Yeah. Yeah, pressure is basically how often and how hard the particles bash into the walls of the container, okay? And if you have a smaller container, the particles are going to bash into the walls more frequently, and therefore the pressure goes up. Yes? Okay. So, if the pressure increases, what happens to the rate of the forward reaction? Remember, the pressure is increasing because we have made the volume smaller. What's going to happen to our forward rate? It's going to increase, yes. Okay, so our forward rate increases because we have the same number of molecules in a smaller space. And therefore there's more collisions, yes. What happens to the rate of the reverse reaction? Yes. Well, if you've got NH3 particles present, you will have a reverse reaction and a reverse rate. We have a closed system, okay? So what we've done is we've taken it from a larger volume like this one to a smaller volume like that. And we have both reactant and product molecules in that container. So what is going to happen to our reverse rate as we squish that container? It is also going to increase because just like the reactant molecules are in a smaller space, the product molecules are also in a smaller space, so you'll have more collisions. So the same thing happens for both of them. So anytime you change the volume, both rates are going to change in the same direction. So if you squish it, both rates are going to get faster. If you expand it, both rates are going to get slower. Now, the reason this causes a shift, though, and it will cause a shift in this case, is that one of the reactions increases more than the other one, okay? And the whole thought process behind this is a little bit tricky. So which rate is increased more, the forward rate or the reverse rate? Anyone got any guesses that they'd like to make? The forward, yeah. We have the side with more gas molecules experiences a greater change in rate. And if this is the only sentence that you take away from the next 5 minutes, that's fine, okay? You don't actually need to go through this whole process, but I'm going to go through it just so that if it helps you, that's great. If it doesn't help you, then just ignore it. Yes? I am. Yes. So, if you take a look, if we have our N2, the coefficient is 1, and for our hydrogen, the coefficient is 3, which gives us a grand total of 4 gas molecules. Yes? For our product, and my apologies here, this should be an NH3, not an NH2. Okay, how many gas molecules do we have on the product side? Just 2 gas molecules. So I'm going to draw this out because I'm not sure that this little table was very useful. If I have my 4, this is my reactants, and I have 4 gas molecules, 1, 2, 3, 4, and let's say that this is a 1 liter container. If I then squish that to a half a liter, so what I'm doing here is I'm halving the concentration, halve being like this kind of halve the concentration, or no, sorry, volume. So I have half the volume. What has happened to the concentration? It has increased, and in fact, it has doubled, right? If you have the volume, you double the concentration. So the concentration doubles. And that's because if we actually do like a little math on that, we can say, okay, I have 4 molecules in 1 liter. That's my original. At the end, after I've squished it to half the volume, I have 4 molecules in 0.5 liters. If I do that division, I get 8 molecules per liter. So I went 4 molecules per liter concentration to 8 molecules per liter. The number of molecules is staying the same, but the concentration is doubling because we have half the space. Yes? Sure. I would, honestly, you're not going to have to do this explanation on a test or a quiz. This is just so that you can picture in your head what's happening, right? Then if we have our products, right, if we look at our products, let's do that in blue, products. Now, how many gas molecules did we have in our products? We did not have 4, we had 2. So let's draw this box again. In this case, we're only going to draw 2 molecules. If this is 1 liter, we have 2 molecules per liter. If again, we cut the volume in half, we still have our 2 molecules, but now it's in 0.5 liters. So now we have 2 molecules in 0.5 liters, which is 4 molecules per liter. So we went from a concentration of 2 molecules per liter to a concentration of 4 molecules per liter. In both cases, the concentration doubled. But which one underwent a bigger change? Is 4 to 8 a bigger change, or is 2 to 4 a bigger change? 4 to 8 is a bigger change. We changed by 4 molecules per liter, whereas in the other one we only changed by 2 molecules per liter. Okay, so this one, the change was and in this one, the change was 2 molecules per liter. And what that means is our change of concentration was bigger for the forward rate. So the rate will be affected more, okay? And what that means is because our concentrations were increasing, that means my forward rate increased more than the reverse rate. They both increased, but the forward rate increased more than the reverse rate. Not that there isn't change for the reverse rate, it's not that it decreases, it's not that it goes the other direction, it is increased, it's just not increased as much. Okie dokie, can I move this or do we want another minute? I can move it. Okay. All right, so which rate increased more? That would have been our forward rate, So what direction does that mean that the equilibrium is shifting? It means it's shifting to the right because our forward rate increased more than our reverse rate. Therefore, we are shifting right. And if you look at it from what's happening to the number of molecules of each type, my N2 and my, whoops, sorry, that should be a 3 there, 3H2 are being used up faster than they are being produced. Yes, the forward direction is using up N2 and H2. So I am losing concentration on the reactant side, and we are making NH3 faster than we're using it up. And these guys we are using faster than we are making. So what that means is we're going to end up with more stuff over here, and we're going to end up with less stuff over here, which means we have shifted to the right, to the products. And just another way of saying that, which reaction is favored? That means which reaction is going faster. That's our forward reaction. Okay, so now we're going to graph, a little graphing. What happens when we decrease the volume of this equilibrium system? Oh, again here, I don't know what was wrong with me. These should all be NH3s, not NH2s. Okay, that right there should be an NH3. If this is a rate diagram that we're doing, what are my axes? Yes? Time and what? Rate. Shockingly, a rate diagram, the other one is rate. Yeah? And guess what the concentration one is? Concentration. And over time. Yes, yes, yes. Okay, so that's quite nice. Yes? Time. Yeah, it's all going to be rate versus time or concentration versus time. Okay? So, starting with our rate, how many lines should we have on our diagram for rate? 2, because what are those 2 lines going to be? Forward and reverse. So my forward, I'm going to put in blue, and my reverse, I'm going to do in like a red dashed line. That's my reverse. Okay. And initially, we're going to say that at the start, we are at equilibrium. So what does that tell you about the forward and reverse rates? Yes? That would be what would happen if we started with only reactants, but we are already at equilibrium. They're both equal, because if we're at equilibrium, the forward rate equals the reverse rate. And yeah, we'll put it somewhere in the middle, okay? So we're just going to be like, okay, here they are, they're equal. Oh, I meant to do that in blue. Okay, and my reverse rate. Now, we squish the container. Everything starts reacting faster. But remember, our forward rate has 4 gas molecules, and our reverse has only 2 gas molecules. So which rate goes up more? Forward. So I'm going to have my forward rate go up more, and my reverse rate go up, you know, halfway or whatever. Okay, just less. So that is our stress. And so we're going to label that stress. We're going to label what happened right there. And what we did is we decreased the volume, which was an increase in pressure. Okay. That looks like TP. That's supposed to be an upward arrow. There we go. Okay. So that was our stress. Now, what does the shift look like? The shift is going to be a curve. And what is the objective of this shift? What is the shift trying to do with our 2 rates? It's trying to make them equal again. So the curves are going to meet in the middle. And if anyone from any of my other classes is watching, this is how much better a lecture goes if I get immediate feedback from you. Just saying. You guys do a great job, by the way. I love it. Okay? It's so much better. My other class, I'm like, oh, we pause. Please answer. Not everybody. There are people who do a good job. Anywho, so here we go. They're going to meet in the middle, and this one, I'm actually going to put a dot here, And I'll explain why in just a moment. Okay, so this goes up. Here we go. And this one goes down. I'm not doing a very good job at drawing that curve. Come on. When you get to this point, you're supposed to ruler it, not for the curving part. Well, it depends. Are you good at drawing a straight line? Because if your straight line looks like that, then yes, you need to use a ruler. If your straight line looks like that, then no, you don't. Yeah? Right? If it doesn't look straight, use a ruler, but only for your test and quiz. Yes? Okay. So, and the reason I put that little dot there is because that dot signifies the change from the stress, the area where we have the stress, to the shift. Okay? No, it's not necessary. The reason I am putting it there is because sometimes people get confused and they think, oh, that's just one great big curve. Yes? Whereas it's not a curve, like here, it's vertical. Yes? That's not a curve, it's vertical, straight up and down. And then we have that curve, and do you remember I told you the change between the stress and the shift should be a sharp corner? It doesn't look like a sharp corner here, does it? So I lied to you a little bit. I am so sorry, okay? But, and that's why sometimes I will put that dot there just so that you know that we're transitioning between the stress and the shift. So we're going from a straight up and down line to a curved line. The important thing is that we still have the steepest rate at the beginning and the shallowest rate near the end of the shift, okay? So that is our rate diagram. Yes? No, not for a rate diagram. The system will, unless you have an open system, but I'm never going to give you one like that. That would be a trick question, yeah, okay? But anytime you have a closed system, it will always go back to an equilibrium state, okay? All right, concentration diagram. Oh, did I move too quick? There we go. Don't ever be shy about asking me to go back, okay? Okay, so our concentration diagram. Again, going to rewrite this equation, N2 plus 3H2 in equilibrium with 2NH3. How many lines will we have on our concentration diagram? We are going to have 3 lines on our concentration diagram. 1, oh, I made that really long. It does not need to be that long. 1, 2, 3. Does it matter where they are exactly? No, it does not, because remember the initial rates are set randomly by Ms. Spence. Okay? No, if it was like if you started with 0, like if you just dumped in some reactants, then you would know an exact you would be given concentration of the reactants and you would know that your products was at 0. Yeah? Initially, yeah. But we're assuming we're at equilibrium and then we're stressing it. Okay? That's for this worksheet anyway. Okay? Initial rates are set randomly. Another word for randomly is arbitrarily. That's a big word. You can just use randomly if you like that better. Okay? Now, again, does it matter which line I label as which? No, it doesn't. I'm going to be lazy and just label them in the order they are in the reaction, N2, H2, and NH3. And remember, we decreased the volume. That was our stress. What happens to all the concentrations? We decrease the volume, so all the concentrations increase. Yeah, the pressure increases. If you increase the volume, all the pressures decrease. If you decrease the pressure, that would be like increasing the volume, and all the concentrations would decrease. Yeah. Now, I'm going to draw these lines to be all the same length. That is a bit of a cheat, because technically, because we have coefficients, you know, the hydrogen should change 3 times as much as the nitrogen. But if we do that, the lines start overlapping each other and it gets really ugly. Yes? So I've even put a note down here to that effect. In an ideal world, we would make the concentration changes due to the stress proportional to the coefficients. But we usually just make them all go up or down by the same amount, because otherwise we're running out of space, things are overlapping, it's ugly. Okay? So just be like, okay, they all go up and they all go up by the same amount. Just makes your life easier. For the shift, we are going to have to worry about the coefficients. Okay, so for the shift, we do need to worry about the coefficients. Now let's just remind ourselves what's happening here. Our forward rate is faster than our reverse rate. So what should be happening to the concentration of NH3 as we shift? Yeah, so while we're shifting, the concentration of NH3 is going to go up. The concentration of N2 is going to go down, and the concentration of H2 is going to go down. While we are here, I'm also going to explain this really quickly in terms of Le Chatelier, because we've done it in terms of rates. What does Le Chatelier say? What is Le Chatelier's principle? Fair enough. Nature tries to cancel out what we do. What we do, nature tries to undo. Is that how you're going to define it on a test? No, it is not. However, let's just think about this. So what did we do to this system? We decreased the volume, which increased the pressure. So what does nature want to do? We increased pressure, so nature wants to decrease pressure. Yes? We brought the pressure up, nature wants to bring the pressure back down again. So if we look at it from that perspective, do we want to shift to the direction which has more gas molecules, or do we want to shift to the direction which has fewer gas molecules? If we want to bring the pressure down, we want to shift to the side with fewer gas molecules. And there's an example on the next page of that. We'll look at that in a moment. But we are going to redefine Le Chatelier's principle, because it is worth doing, because if you write on your test what you do, nature tries to undo, you're not going to get credit for that. So you might get a half a mark. A system oh, I should say when a system, sorry, when a system at equilibrium is subjected to a stress. Let's use the words, let's use the chemistry words, a stress. But you're right, a change. What's the system going to do? How does it do that? The system will, how is it going to counteract it? It's going to shift. Yes. In order to, you can say minimize the stress, you could say counteract the stress. Yes, of course. Okay, so go home and like write that down every night before you go to bed between now and the test. Okay? Like every night, just write it down. Okay, so there we are. That is Le Chatelier's principle. This is why you should always have a piece of blank paper beside you too, because I sometimes go off the page. Whoopsie. Because my page is long. Look, I could keep going. Woo! I could go way over there. No. Okay. Sorry about that. Yeah. Trying to cram it in. And it's like, where is it? Where am I going to have room for this? Oh my God. Yeah, I know. I'm sorry. I should leave more space, but part of me is like, oh, I'm photocopied too much. I should like try and fit as much on the pages. So there's this like war in me as to how much space to leave. I don't know. That's true. I should just in for a penny, in for a pound, right? Yeah. Okay. No, that's true. They are not. They are not. All right, but we could return them into paper as long as we recycle them at the end of this. Yes? Okay, good. So they have all gone up, and we agreed that we are shifting to the right, so we are making NH3. So I'm going to draw my little dot there just to say, okay, I know, just for, you know, it's going to go up, 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 up. Yeah? It's always shifting by proportional amount. So is H going to change by the same amount as NH3? No, it's going to change by a different amount. And a nice way to say this is if that's a 2, it's nice to label this change as 2x. You know what I mean? Because that way I don't have to be like, oh, it's 3/2 x. Like, you know, just go with whatever the coefficient says. So that's 2x. Hydrogen I'll do in a different color because it's going to overlap and it'll make it a little clearer. By how much should hydrogen change? 3x. Downwards, yes. And actually that should have, I made that way too long. It should actually level out at the same place as that other one. There we go. So that's going to be 1, 2, 3x. Why does it go down? Because when we go to the right, we are making NH3, yes? What are we making it out of? We're making it out of N2 and H2. So those N2 and H2 get used up to make the NH3. Does that make sense? Yeah, yeah. Yeah, exactly. If it looked exactly the same and you labeled it 3x, I'd be like, bingo, okay? Now, how about N2? Is N2 going up or down? It's going to go down as well because every time you use up an H2, you need to use up an N2 to react with it. And it'll go down by how much? 1x, okay? So here we go. Alrighty? Good. And you can see, even though there's not really like a sharp corner there, there is a difference between vertical and curving. Yeah? Now, this is just to illustrate from a Le Chatelier's principle what is going on, okay? So we have the reaction, we have 2NO2 becomes an N2O4. Okay, so 2NO2 goes to N2O4. So for our, I'm just going to go all the way out here so you can see all of these at once on here. You'll be able to see them all at once on your paper. This is a syringe. Okay, so if you're wondering what that is, it's a syringe. And we're going to put a stopper on the end of that syringe so that nothing can get out. So when we press the plunger on that syringe, nothing is escaping, so everything's just getting squashed. So in our first syringe, we are at equilibrium. In our second one, what we have done is we have compressed it. Yes? Not if I'm pushing on it. Yeah? Yeah. Yeah, no, you would push it down. Sometimes people will put weights on top, so it's just like a consistent force rather than, you know, when you push with your hands, sometimes it's a little hard, but you would put like a certain amount of bricks on it or something. Yeah. Okay, so now we have our stress. And what we've done is we've decreased the volume, so we have increased our pressure. And what we're going to do now is before we go to, this is like the new equilibrium, and this is going to be our shift. Now we're going to zoom in. Yes. Yes. Exactly. The stress is the change in something, and then the shift is adjusting to that something. Yes. So we're going to zoom in now. Yes? Yeah, you're like, what? Okay. So what I'm going to get you to do is I'm going to get you to circle your N2O4s in each of these. Just because it makes it easier to spot them, yes? So if we were to now go and count, let's start with our N2O4s. How many N2O4s in our first situation? Just the one. How many in our second situation? Just the one, because all we've done, that is our stress. Before there's been any shifting, right? We still have that one. Now, the system at that point says, the stress is, the pressure is too high. How could I fix that? Well, we could take two of these and form one of those. Yes? And we could take two of these to form one of those. And what that means now is that our total number of particles has gone down. And that means that our pressure decreases again. So here we had, yes, Rade, sorry. The stress is short-lived, and it's what we do to the system. So I have to tell you what the stress was. The shift is what you can predict based on the stress. Yeah. So the stress was a decrease in volume, or also an increase in pressure. And during that stress, we still have the same number of molecules. Now let's just count up how many of our NO2s we have. We have 1, 2, 3, 4, 5, 6, 7, 8. And over here we still have 1, 2, 3, 4, 5, 6, 7, 8. Uh-oh. I think I drew one too many. Cross one out. Ah, there we go. Okay, better? All right. So we have 8 of those, and now we still have 8 because we crossed out the one that I put in by accident. And that gives us a total of 9 molecules at the beginning, 9 molecules while we are stressed, and that means our pressure has gone up. And now the system is going to shift, and that's what's happening when we're using up the NO2s to make the N2O4s. This is our shift. And the shift uses up, in this case, a total of 4 NO2s to make 2 extra N2O4s. So now we have 3 N2O4s and only 2 NO2s, which gives us 5 molecules, and therefore our pressure has gone back down again. This is what we do. The stress, and this is what nature does. Yes. Okay, are you ever going to have to do this kind of thing where you're like actually drawing the particles? No, it's just to help you visualize what's going on in terms of Le Chatelier, okay? So to summarize here, the stress was an increase in pressure due to the decrease in volume. And so the system shifts to the side with less or fewer gas molecules in order to bring the pressure back down. I had a little dyslexic moment where I wasn't sure which side I was going to put the little thing on the D. That's never happened to me before. I think as I'm getting older, my brain cells are dying. That must be really frustrating to have to live with on a daily basis, like for people who are dyslexic. Like I've like just in that one moment, I was like, holy, where do I put it? And it took, and I'm like, God, that must be so frustrating to have to deal with that every day, every moment. Oh. Anyway, respect for people who have to work with that every day. All right, so therefore, if we have fewer molecules, that means we're going to have fewer collisions with the sides of the container, and therefore the pressure is going to go down again, which is what we wanted. All right, and we have 5 minutes left, so I'm just going to quickly tell you your homework, and then we might go through the, you know what, this is as far as I got with my other class, so we're just going to call it a day there. So your homework is number 1, if you did not complete the lab setup, you are going to complete the lab setup, so that complete the lab setup. Is there anyone, be honest with me, I'm not going to like yell at you or anything. Is there anyone who did not complete 2.2b? If you did not complete 2.2b, you are going to complete 2.2b, okay? Complete 2.2b, yeah, I think so. That sounds right. Okay, so tonight is a catch-up night. And I see you guys on Thursday, yes? Okay, good stuff. Whew.